Hello, can people hear me? Everyone can hear me? Cool. All right, let's get started. I am not Matthew Reuter. I'm David. I'm the graduate TA. We can move past the fact that I am blatantly using his material. He gave me permission to do so, but okay. So this is a great little thing that Professor Reuter does. It's really hard to read in class, but if you want, what he does is there's like an interesting like mind game sort of puzzle that he gives at the beginning of each of these slides. They're great if you're going back to the slides that you've already seen on Blackboard or something like that. Unfortunately, as someone who's always sitting in the back of the room, like I don't even know if it's possible to read it from like the first row, but there's this there are interesting puzzles, and you should, if you have free time and are particularly nerdy like me, you might be interested in taking a look, but yes. Okay. So this is what we're going to do today. We're going to just briefly talk about what we mentioned on Tuesday about applied math, why it has that word applied in it, and why it has that word math in it. And then we're going to start with our first unit, which is on GPS. Show of hands, who has heard of or reads the comic XKCD? Anyone? Okay, so we have a couple. It's a great comic. It's a very geeky comic. Another thing that's great to read when you have the Blackboard slides in front of you, but is kind of hard to read when you're far in the back. Anyways, this is an XKCD that's making a joke about what it means to do applied work. And so to ruin the joke, I'll explain it a little bit. There's these scientists line up. You have a sociologist, a psychologist, a biologist, a chemist, a physicist, and ignore the person on the side. And the joke is that each person to the right is saying, you know, whoever's standing to the left of me, their field is basically just my field in an applied setting. And it gets all the way to the point where the physicist says, well, basically all of that is applied physics, which means that I'm the best. And then noticeably farther away, there's the mathematician who says, oh, I didn't see you guys over there. It's funnier when it's not explained. OK. So just to read the red highlighted stuff. This is, again, from the Princeton Companion. Perhaps the most succinct and correct way of talking about applied math is that what it really is doing is bridging the world of pure math to the world of science and technology. And that's a good way of thinking about it, because frequently it's not the nature of the problems, it's where they arise. And that's an important distinction. Okay. And because this course is more focused on the technologies, what we're going to do is start with a technology and investigate it from a mathematical perspective and come up with, you know, a couple ideas that can be represented in some sort of mathematical way and study those things. But this is not an engineering course. Everyone's sigh of relief. We're not going to get into crazy detail, including even when we talk later about the term paper. Crazy detail is not what we're going for. But the idea is to be able to identify some meaningful connection between the mathematics on the one side, or on this side, and technology on that side. So basically what I just said. But anyways, what we're going to do is we're going to pick a technology. And by that, I mean we're going to pick a technology, except for the term paper, where you get to pick a technology. And we're going to talk about why it's important, why the technology itself exists, and sort of how it comes about, and where it is currently used. And I should just take a brief aside to say, in this day and age, in 2018, when we say technology, we think of computers, right, of some kind. But until 1960, 1970, when people said technology, they meant this huge array of devices and ideas that could essentially improve some function that we do on our own, right? And so that could be anything from a book to like a chalkboard or whiteboard, or to a smartphone, right? So we're talking technology in the most wide sense that you can think of. And so what we're going to do is we're going to ask a couple questions, about how the technology works. And from there, we're going to be able to, or work hard to identify a math concept or two that allows us to do some analysis, to sort of understand how it works. And from there, we can actually build an understanding, a real understanding of the system that the math is supposed to be representing. And we can show that this works by, giving examples. And then, ideally, we'll be able to answer the question that we started with. Not necessarily going to happen, but that's what science is all about. And so, the buzzword is critical analysis skills. It means taking a moment to ask silly questions and simple questions and making sure that we have really great answers to those things. And it turns out that sophistication means realizing a simple question is the important question. So with all that said, I'm going to take a step back, and I am going to need y'all's participation today. So what I first require is that you turn to the person sitting next to you and give your names. And if you could be a dessert or a desert, what would you be? And so let's do like 30 seconds of that, please. So just, yes. All right, let's bring it back. Okay, just a show of hands, who gave a desert? Anyone give a desert? Did anyone give Antarctica? Because that would be my guess. All right, maybe someone knows better than me, but I think Antarctica is a desert because a desert is determined by the amount of precipitation, and it basically doesn't do any of that in Antarctica. So anyways, that would be my desert, unless I'm wrong. If someone knows I'm wrong, then okay, cool. Okay, so where are you? Turn and talk for like a minute. We're going to just generate answers, right? As philosophical or as practical as you want to be, turn to your neighbor and discuss this question. All right, let's bring it back. So does anyone want to volunteer some answers to this question? Any takers? Yeah.
So I thought it was important to ask also in the context of time. So like, if we are in a country that exists, or if we're in an area that had a country in the 1940s and then that country doesn't exist anymore, we are now in whatever that new area is called.
So you're saying that in this particular location, 100 years from now might not be the state of New York, right? And so to say that we're in New York is problematic unless we give a time for when we're there. How do people think about that? Interesting. Any other suggestions? All right, well, let's give some more prompts here. So one response could be that we're at AMS 103, right? It's 8:40 in the morning, and we're all wishing we were asleep. And we're also at Stony Brook University, right? That is a useful way of telling a person who is not at Stony Brook University where we might be, right? It's not super useful for someone else, you know, in Harriman or something, right, to say that we're at Stony Brook. It's like, thanks. But AMS 103, okay, that's a pretty good. There's only, what, 100 people, right, who could possibly say that right now, so that's pretty good. A question that I don't have the ability and the background to answer or even approach is, how do we actually know that that's where we are, right? We could really take a step into the what is knowledge question here, but we're not, so sorry. And instead, how do you find out where you are, right? This is a important practical consideration. So how do we figure out where we are? Does anyone have any suggestions? Right? How do you figure out where you are? Right? If any of you are bad at navigating in a car or something like that, like, what do you do? Yeah. Oh, you ask someone. Okay, that's a good answer. Yeah. Titles such as? Oh, okay. So you have some sort of location that you're looking for, which you know exists. Street names. Okay, good ideas. Yeah. You open up your phone. Okay, so we're gonna culminate with that. Now, suppose that you didn't have a phone, and suppose that there aren't any noticeable landmarks. How would you go about finding out where you are? You could use stars, right? And that's actually the classical historical way that navigators on the oceans would figure out where they were. They would use actually fairly complicated techniques of using the relative position of known stars to determine where they are relative to, you know, where they set off and where they're headed. Yeah. Yes, the position of the sun. Although it turns out, like, I use that frequently as a like a heuristic, but it can also be very wrong depending on where you are on the Earth. So just so you know, if you think that the sun is in the east because it's the morning or something like that, like it's in the direction of the east, but it's not necessarily east, which I've found is very frustrating because I get lost that way. Anyways, enough about me. So landmarks, right, a very important thing, right? If you're in South Dakota and you see Mount Rushmore, you kind of know where you are, and also, you know, street signs. But the classical way of doing this, like with celestial navigation, is by looking at stars. And this is actually one of the earliest mathematical developments, was getting a rigorous understanding of how the stars move around, which has very practical significance. Okay, but we don't use the stars. There's one huge weakness for using the stars to navigate. Can anyone give me the one huge weakness? Yeah. Could be cloudy. It could also be the day, right? And like, so it's only good around 12 hours, right? So we need something a little bit better, especially the US Department of Defense needs something a little bit better. And so what we have today is something called Global Positioning System, GPS, which I will take a bet that most everyone here is familiar with that acronym. So the way that it works at a high level, and by the way, you should check out the Trimble tutorial here. If you go to the, if you just follow this link by typing it in, or if you like view these slides later, you can just click on them. This is a great tutorial. It also has animations if you have a Flash player. I don't have a Flash player, so I didn't get to see the great animations, but I am told that there are great animations. So go to Trimble, and a lot of this stuff will be reviewed, and there will even be more information if you're interested. So the way that works is we have roughly 24 satellites orbiting the Earth, which we've launched in the last 30, 40 years. Actually, we might have more because we want to have redundancy. The US government is very good at making sure that we have redundancy. And what they do is they are actually, it's the same concept as stars, right? Because the way that stars you can think of being used is that the Earth is rotating around itself, but it's also moving around in a circular-like shape, right? So in a similar principle, we can use these artificial stars to sort of create that at a much quicker update speed, right? Instead of waiting every 12 hours, right? You can get very accurate information within seconds, which is ideal. And when you have really, really good GPS, we can be absurdly accurate. And of course, I have never had a use for GPS that's accurate than a cubic centimeter or a square centimeter, but I'm sure that the military has one. So as I've alluded to, we have had issues with with localization in a military context, right? And during the Cold War, what the United States military was primarily doing in order to sort of, for intelligence and whatnot, and if there's someone who knows more about this, I apologize for butchering this. But anyways, so what we needed to know from a command level is where all of the ships are, where all of the planes are, and where the missiles need to be going if the worst happens. And so, starting in 1973, which is 45 years ago, wow, 45 years ago, the Department of Defense started a $12 billion project to come up with a satellite-based system for determining location accurately. And this was finished in 1995, so that was, what, 23 years ago? Yeah, okay. So basically what happens is these satellites are orbiting around the Earth, and they receive signals. And from those signals, they send back responses, or they're pulsing out, they're sending out emitting responses. And then from anything on the ground, we can use a combined number of these satellites to actually figure out where that location on the ground is based on the information that the satellites are giving. So to do this, it's a 5-step procedure. So at a high level, what we're doing is triangulation. And it's in quotes we'll see in either this lecture or the next lecture. So basically what happens is a receiver measures the distance from radio signals from the GPS. And so what happens in practice is that the GPS satellites needs some way of getting very accurate timing. And there are some ways that it goes about doing that. If, for example, the information was being read as receiving data in 1 second when it was actually half a second, what that means for the calculations, as we will see, is wildly different locations on the planet. So we need a very high degree of accuracy. You also need to know where the satellites are in space. And so the way that this goes about is we understand how things that orbit the Earth actually behave. And when you combine that with careful collection of data and all that, we actually have a very good model for where all the satellites are. And then there's other issues. There's the fact that if a signal travels through heavier substances in some sense, there can be distortions, right? And so if you're using data to figure out where you are, and the data there's noise on it, right? You have to be able to identify where the signal is. Okay. So from the question, so I mentioned that the U.S. government is concerned about redundancy. But the first thing that you need to do before you can even talk about redundancy is something else called sufficiency, right? So really, from any point on the Earth, how many satellites, let's say in perfect conditions, do we actually need in order to be able to figure out where we are? So the way that we're going to solve this problem is by building a model, a mathematical model. And what we will first attempt to do is identify the mathematical concepts that are necessary in order to understand and build a model. So, okay, so the first one, relationship between speed, distance, and time. This is a physics thing. It's like a math thing. This is actually a great example for the term paper. You can't write a term paper about the relationship between speed, distance, and time because those are all physics ideas. They're not mathematical ideas. We also need to know what this whole triangulating business is. And of course, when we talk about triangulation, we're actually talking about trilateration, which we will get to. We will also need to understand a little bit about systems of equations, and finally, coordinate systems. And all of those will be discussed in turn. Any questions before proceeding? Okay. All right, so we'll talk about the physics thing first. So speed and distance, and if you want to get like all pedantic with your vectors, okay, we're talking about velocity and displacement. So the velocity when you're, or the displacement when you're running around in a circle is 0. I get it. Okay. So what we need to do is understand at a basic level what this physics equation is getting at, right? So when we talk about speed, right, we're talking about how far you can go in a certain amount of time, right? That is the notion of speed. And if you look at the units, right, we're talking about some unit of distance divided by some unit of time. And in fact, that is exactly what speed is. And we're all hopefully, at least like familiar at a intuitive level of what speed is. And of course, we can translate this into math mode, right, where you have the speed, the distance, and the time. Of course, once this equation holds and we agree that it works, it doesn't matter how you write it, right? Any valid manipulation. So sometimes if you need distance or if you need time, you can just rearrange as necessary. Yeah. Okay. This is all physics, right? The difference is that the math concept here is being able to like multiply and divide, right? That's not what we're looking for, as a heads up. Okay, so let's do an example. Let's say it takes you 10 minutes to drive from Stony Brook University to the Smith Haven Mall. And what we want to do is figure out what the average speed is. So turn to your neighbor, and let's solve this problem. I should also note, you can use the internet. Okay, have we all attempted at least a way of doing this? Okay. So someone volunteer how we start with this problem, right? What did we do? Yeah.
Find the distance.
Okay, and what is the distance?
3.4 and 3.5 miles.
All right, let's distance. Oh my gosh, okay. Distance is equal to, let's just do 3.4, why not? Miles? Okay. And time. What do we do with the time? Yeah. Okay. So first of all, we have time that was given in the problem, right? Which was 10 minutes. And how did you convert that to seconds? Okay, so you could do, 60 seconds divided by minute. And you get something like 600 seconds. Okay. 600. Okay. And then to calculate the speed, what do you do? Yeah.
I just took 3.4 divided by 10.
Okay. So in the world where you're interested in your miles per minute, you would just take 3.4 miles divided by 10 minutes, and that would be your speed. And that ends you at what, 0.34 miles per minute? Okay, and if we wanted to put it in miles per hour, which is a more what we're colloquially used to when we talk about speed, what would we do from here? Yeah. Okay, so, and I think that being a stickler for units is a really great way of checking your work. So I'm going to continue using units. 60 minutes per hour, and the minutes cancel like that. And so this is roughly what? All right, I'm hearing 20. Okay, so not super fast, but then again, you have stoplights and all those things. All right, let's see how we did. Nope, that's not it. Nope, that's not it. Nope, hold on. There we go. So he says 19.8. And the reason, by the way, is because he took the distance as 3.3 miles. So it just depends on what you mean by the distance. And there's a totally valid debate about that. But he did the same process, right? Okay. Let's do a more fun example. So we have this satellite, and it's got an average altitude of 11,000 miles. And it emits a radio signal. How long will it take for the signal to reach the spot directly underneath the satellite? That's our next question. Talk, come on. It's not fun doing these things on your own. All right, let's bring it back. So someone help me out. Yeah.
I converted the miles into meters
Okay.
with the meters per second unit of the speed of light.
Okay.
And
So what is the first of all, what's the distance in miles?
the distance in miles is 1,000.
Okay, and then what is it in meters?
Was it 17,702,000?
Oh, what's the conversion from miles to meters?
Oh, I'm not sure.
Okay, does anyone know offhand?
It's 186
6 2. Oh, okay. Does anyone know the conversion from, and by no, I mean, does anyone have a phone that can Google? Yeah. 1609. That sounds right, because it's 1600 in track. Okay. Meters per mile. Miles cancel, and what does this end up with?
Let me just double check that.
Okay. Does anyone know offhand? I mean, by know offhand, I mean plug it in. Okay. Yeah. Okay. We'll hold on to that. We're going to try the meters way. Yeah. What is it?
It's
17,699,000 meters. Okay, that seems plausible. Okay, and what's the speed of light in meters per second?
299.792458.
Okay, it's 3 times 10 to the 8. Oops. Meters per second. Second. Okay. And so the time is just by rearranging, right? Time is just distance divided by speed. This is the switcheroo in with fractions. Anyways, so we get 11,000. Oh, nope, that's wrong. 17,699. 17,699. Okay, this is 700 now. Meters divided by 300. 0.00000 meters per second. What's the unit going to be on this? Okay. And what is this number? 0.06 seconds. Okay. And did you get that when you did miles? Sounds pretty good to me. So the point is that it doesn't matter as long as you're consistent. You should get the right answer, right? Which is actually kind of nice. It means that there's multiple ways to do things, or intimidating. I don't know. So let's see what we got here. Okay, cool. But what's the problem with this? This does actually have an implication for us. If we're talking about 6/100ths of a second being the relative accuracy that we need, this is a lot, right? So in order to be able to do this well, we're going to need very accurate satellites, or at least very accurate clocks on the satellites. Okay, so now let's further examine this idea of distance, right? So what we just did in the previous problem was we assumed, can I like move this around? Is that a valid thing here? Let's see. So what we assumed here is we got this like nice satellite up here. You know, okay, that's my satellite. And then we've got the Earth's surface, and it sends out a signal in all these directions, right? But we only cared about the one right here, where it reaches right here. And if that was our problem, life would be really good, but it's not our problem, right? Because first of all, this is a picture and not the real world, and second of all, it could be any place on a sphere, right? So we have to talk about the distance between points in a non-trivial way. Okay. So it turns out that the natural way of talking about distance, although not the only way, in one dimension is simply just look at, you know, where the 2 points are and consider their difference. And if it's negative, okay, we're not talking about negative distance, right? And it works the same way in 2 dimensions, right? That's the Pythagorean theorem for triangles, if anyone right triangles in particular. And it turns out that the way that it works in 3 dimensions and more is you just add terms to this Pythagorean theorem. So what I mean by that is, if you note here that you have this like x-coordinate difference and the y-coordinate difference, when you go to 3 dimensions, you just add the z-coordinate difference. And so, yeah, it's like you should just have a general idea of like that this is the way that you compute distance. So with that said, this is not going to be so bad. Let's do this. Let's give like 30 seconds. People talk. People talk. Please. What? What the heck? What the heck? Okay, we're doing this now. Does anyone remember what these were? All right, I'm checking. Negative 2, 2, 13. Why did that? Oh. Okay, how do we do this? Anyone want to suggest a way? Plug it in? Okay, great. I'm going to plug it in. So we've got 3 minus, oh great, minus 2 squared plus 2 minus 2 squared plus 1 minus 13 squared. Okay, and this looks like a square root of 5 squared, and that looks like a 0 squared, and that looks like a 12 squared. And, of course, that is 13, and I'm sure all of you know that, right? No, I'm just kidding. It's a Pythagorean triple. So that's the distance. Should you ever be worried that the distance is going to be negative? Or are you confident that it's going to be positive? Something to think about. Okay. Cool. Wow, he did units. Wow. Okay. So we talked about triangulating between satellites. That's like the way that we all use the word, but actually triangulation is not that. Triangulation is when you have a slightly related but different situation where you have 2 points on like a shore, and you use that to find out what the distance between the shore and a moving ship is, right? It's a nice idea and it's very useful. It's just not the one that we need, right? Because the problem is that instead of that, we have a fixed ship and moving satellites. So it's actually, triangulation is a cool but not useful idea. Not useful for our purposes. It's great for making maps and all that. So what we actually need to do has a much cooler picture, and it's called trilateration. And so basically what we're going to do is we're going to try to find any spot of these circles that are being created, or spheres being created, that are all being hit simultaneously. And that's what we're going to talk about as finding the distance. So you can be a snob at dinner parties now and say, well, actually, it's trilateration, not triangulation. That's exactly what I did when I found this out. So, you know, that's just, it's condemning for me. But anyways, so let's think about this model, right? And one important idea in doing math is you should always ask, what is the easiest thing that we don't know how to do? And since we're starting a completely new topic, we're going to say, what is the easiest thing that we don't know how to do? And that's finding the distance of a signal in one dimension. Right? Okay, we're going to try eventually to be in 3 dimensions, but that's hard. So let's stick with easy and learn from this. So we have a satellite, and it's at the origin of the number line. It sends out a signal, and we know that the signal moves at 4 miles per second. And we know that we receive the signal 3 seconds later. The question is, what is your position? All right, go communicate, talk, and figure this out. Okay, so what do we do here? Does anyone have any thoughts about how to, well, what is this problem asking? What are we looking for? Can someone give me an answer to that? Yeah. Displacement from the origin. Okay. What do we know how to, what can we actually calculate right now? We can calculate the distance. If we interpret received at as the time, right? Well, the distance, make sure I get this right, distance is equal to speed times time, right? Okay, well, from there we just plug in 4 miles per second times 3 seconds is equal to 12 miles. Okay, so what this tells us is that if we have a satellite that's at the origin and it sends out a signal and we receive it and all that stuff, then we know that we are distance 12 from the satellite. Okay, so where are we? Any thoughts? Became very quiet, yeah.
Isn't the only thing we know is that we're 12 miles from the origin?
That's correct. Okay, so you're suggesting that we don't know our displacement? Do we know possible displacements? Okay, so possible displacements. Let's put this over here. possible. So what are the possible displacements? Yeah. Mm-hmm. Okay, so that's actually a great idea. Let's just talk about that for a second. Am I extending the page? Extend, oh. Extend, okay, cool. So we've got the picture, right? Here's the origin, right? And the suggestion was to draw a circle. So basically, we could draw a circle like this. If that were a circle, that would be great, right? And we would say, well, we're on the number line, and we're 12 units away, right? So what does that mean? Well, in order to be 12 units away, you have to be somewhere on the circle. And in order to be on the number line, you're either here or here. And what are those points? Sorry, say that again. So remember the, oh, wait, do you mean like this and this, or do you mean this? Sorry. The other two. Okay, so remember that this is a speed and that's a time, but we're interested in where we're located. And so one way of verifying that is just to look at the units that we're talking about. We want to find where we are, which is the location, which means like units of distance, right? Yes. Yes. Okay. And this is a great place to mention. We could be at distance negative 12. What the heck does that mean? It means, in this case, that we're 12 units to the left, right? Negative signs when it comes to physics and the way that it works in the mathematics, it just means direction, right? So you could be moving this way or that way. So don't get too freaked out. If your distance is negative, get freaked out. Okay. Why won't, okay. So our possible locations right now are negative 12 and 12. Those are miles. So we don't know where we are exactly, although we've narrowed it down quite a bit. Okay, so let's make our problem a little bit more interesting. Suppose that we also have a different satellite located in a different location. It has the same properties, meaning it sends the signal at the same speed as the first satellite. But you receive the signal at a different location. All right, also, they're sending the signal out at the same time, right? Now can we figure out where we are? Discuss, work on this, please. What was it? Negative 4, and then 2 seconds. So speed is still 4, right? 4 meters per second, or miles? And we received at 2 seconds. Okay, now this is the same problem as before, right? The way that we figure out our possible locations, it's identical, right? They're just two satellites doing their own thing. We can use the same process, right? So the distance is equal to the, let's see, speed times the time, which in this case is 4, wow, okay, miles per second. Let's see, can I go like that? cool, times 2 seconds, which is equal to 8 miles, right? So we know that our distance from the second satellite is 8 miles, right? So what does that mean in terms of where we might be relative to the second satellite? Well, in a similar way, right, there's 2 possible locations from the same like kind of circle argument, right, from before. So what are those 2 possible locations? Okay, so we have 2 ideas here. One is -8 and 8, and the other is -12 and 4, did I hear? Okay. So someone who believes -8 and 8, can someone explain their reasoning? And then we'll do the other one. Any thoughts? Anyone want to take a stab at -8 and 8? Yeah. Okay. Okay, so basically it's right. We know that we're 8 units away, so we're 8 units away from. Well, what are we 8 units away from? Yeah. Right. So the satellite located at -4. So what's actually going on here? Let's see if I can extend this without ruining everything again. Okay. So we know that the distance is 8. But we also know how to calculate distance, right? It's, well, our location, we'll call it x, and the satellite's location, which is -4, yeah? Equals, right, x plus 4. Did I do that? Yeah. Right? Did I do that right? X minus -4. Yeah, that's correct. Okay, so one way that we can view the problem that we're doing is we're actually solving this equation, right? This is equal to 8. It wasn't super intuitive that that's what we were doing, but that's in fact what we are doing. So what is the solution to this equation, or alternatively, where are the possible locations that we are, based on the idea that we're 8 units away from the location -4? Like, you can reason this out without doing any math. Yeah. So -12 and 4. So this, so just to say, this is this is not the right origin, right? So this is satellite 1. That would be satellite 1, whereas this is satellite 2. Okay, so that means that our possible locations are now -12 and 12 for the first satellite, and -12. No, stop. No, what do you do? Come on. Okay, 12 and 4 for the second satellite. Okay, so where are we? We're at -12. Now, why aren't we at 4? Can someone justify why we are not at 4? Yeah.
Because the possible locations for the 2 satellites have to line up.
And why is that?
Because we're sort of, like, I don't know if this would necessarily be triangulation, but we're taking the 2 sets and finding where they intersect on a 1D plane.
Right. So this is a great idea, and let me just elaborate even more. The problem is that we have this thing called reality, and for the sake of mathematics, again, I'm not a philosopher, but for the sake of mathematics, there's objective reality, right? And we've observed with very accurate information that we're either, based on the data from satellite 1, we're either at -12 or 12, and from the data from satellite 2, we're at -12 or 4. It has to be one of those, and it's just not consistent with reality for us to be living in the world where our location is 4. Right? Because then the speed of light is not working correctly, and like all sorts of hell breaks loose. This is bad, right? So when you think about what we're doing here, one perspective on it is we just need to be consistent. And the only way to be consistent is that we're at -12. Does that make sense? Any questions? Yeah. Okay, so the idea that's really going on here is that we're concerned about consistency. We have data which suggests that we could be at any one of these 4 locations. But we know that they're happening at the same time, right? It's not 2 different universes that we live in, right? It's the same world, the same physics, we must be simultaneously experiencing the satellite information from satellite 1 and the satellite information from satellite 2, and both of them have to be correct, right? So there is a way of understanding our data so that everything is consistent. And the only way that that happens is if our location is at -12. It's not possible to be consistent and our location is at 12, right? That's the conclusion. So there's the three ways that I will say that you can interpret the mathematics here. One is there's an equation and we solved it, right? And there's another equation and we solved that. And when the two equations are being solved at the same time, that's our solution. Another way is what I'm talking about more kind of abstractly. There's this notion of everything needs to work, right? 1 is equal to 1, right? 1 plus 1 does not equal 4, right? And if we don't want a world where 1 plus 1 equals 4, we have to be at -12, right? So that's one way of thinking about it. Another way is just doing the math. A third way is just pointing out, well, actually what's going on here really is we've got, full screen, is we've got some lines, right? And we know that if we satisfy one of the equations, well, technically it's not a line, whatever, this is an analogy. If we satisfy one of the equations, then we're on one of the lines, right? So suppose that we satisfy this first equation, that means physically that we're on the line somewhere, but we don't know where. It could be anywhere on the line. But if we also can satisfy a second equation, meaning that we're anywhere on the blue line as well as on the red line, right? The only way to work with both of that is if we're intersecting, right? So there's three views. There's the view that these are systems of equations which can be solved algebraically, which means that whatever you get that satisfies both is the correct answer. There's the abstract view, which is in order for math to make sense, it has to be that we're at -12. And then there's the geometric view. We're on two lines, or we're on two circles, and the only way that we could be on them both is where they intersect. And so I've met people who really prefer the first way and really prefer the third way. I prefer the second way. Whatever works for you in interpreting the result, please use, right? It's very good to do what actually helps you. It should be pointed out that we could have a third line, right? And it's possible that, as in this case, you can be on all three lines at the same time, right? Namely, at their intersection. The analogy is if we had a third satellite that gave us information that told us that we were at -12. Okay, we have a third satellite. It's redundant, but whatever. It tells us that we're at -12. What gets more interesting is if you have something like this. Now what's going on? Right? I just made this whole, I waxed polemic about why it's important that math is consistent. And now I'm saying we have data from 3 satellites, and it's not possible for all 3 of them to be right at the same time. Why? Because there's no way to be on that line, or the intersection of all 3 lines simultaneously. So this might cause some bother, but we might just say, well, there's error, right? There's noise, there's all sorts of things, and that might account for the discrepancy. If we lived in the real, perfect physics utopia, right, we would be here. But we're not, because we live in the real world, and so we're getting something like this, and we're going to have to interpret that, right? But that's not what we're super interested in right now. Okay, -12 miles. And so what it turns out is if you had 2 satellites, and we lived in 1D world, that would be sufficient to find out where you are at any place on the line. So we're not going to do this one because I just kind of talked through it. If you had a second satellite and you had all of this data that was generated from the second satellite, it turns out that it would not be possible to reconcile the 2 satellites. This one says that you're either at 11 or you're at 5, right? Or -11 or you're at 5. So it doesn't correspond to anything that we knew from the first problem, from the first satellite. And that's a problem, right? That means that math isn't consistent, everything, all hell breaks loose, divide by 0, all that stuff. Something's wrong. And it could be noise. So what we've actually done is we've done another thing, which perhaps we've alluded to, but we haven't made explicit. We have two models. Can someone give me both of the models that we're using right now? So we have one model which says that distance, time, and speed are related. Yeah, and we did very, similar problems about, dividing distance by time and multiplying time and speed and whatever, right? We have an equation that says that they're related, right? But we said that our physical problem that we're trying to solve, namely identifying where we are relative to satellites, is not going to be so nice that we can just know the distance, right? We're actually going to have to do some work for the distance. So we have a model for our relationship to the satellite via via distance and time and things like that. But we actually need a better model to understand the notion of distance, and that's where we have the distance formula. All right, so what we've done here is we've merged two models together. And essentially what we've done in this one-dimensional example, you notice that this is the one-dimensional distance formula, right? Is we've solved these two equations. Right? It didn't feel like we did it, but that's what we did. And so this is generally what is called a system of equations. I don't really understand why it's called a system. Sometimes they're called simultaneous equations. I kind of like that better because it means that in order to work, everything has to be at the same time. Everything has to work at the same moment. But anyways, what it means is you have two equations, and we will say that there's a solution to those equations if there's a solution to one that is also a solution to the other. Right? Is there any discomfort with that idea? Because this is very important, and I'm perfectly fine to take more time on this. Okay. Yes, solution. I'm very good at predicting what the slide next is going to be. Anywho, a solution has to be a solution for both equations at the same time. So it's not good enough that 4 is a solution to equation 1 and 12 is a solution to equation 2. Right? They're not the same. They can't solve it at the same time. Negative 12 can solve both at the same time, and that's what a solution is. And this will be true if we have 3 equations and 4 unknowns. This will be true if we have 1 million equations and 2 million unknowns. By the way, that's how CT scanners work. Right? So a solution means every equation has to be satisfied by the same number or the same object. Okay. And just to point this out, the equations don't have to be, nice, pretty lines, right, which you may have seen from high school. In the case that we're going to be more interested in are cases where the equations are circles. Now, before I get into this, do you know that there's a distance way of interpreting a circle? So just to say a little bit more, if I have an origin, and the origin is a satellite, and it emits a signal in all directions, right? And I freeze time at, say, time 1, right? All of the possible locations where that signal could be after 1 second forms a circle. Is there some intuition as to why that's working? Basically, all of the points here are determined by being the same distance away from a common center. So when you think about distances in a sort of abstract way, you can think about circles, because what we're really talking about is circles. And that's why we had that picture from before. Let's see if I can find it. we have these spheres. Okay, a sphere is a three-dimensional circle, right? But the idea is that we're talking about distances, and when we say distances, we're talking about circles or spheres. And so just like in the case where we were working on and it had some absolute values and grossness, right, we could also have something more complicated where you have two circles. And we're saying that the distance from the red circle, no, come on, I want to, why is this hard? The distance from the red circle, that is also the distance from the blue circle simultaneously for like a fixed time, right, 1 second. Right? In order for that to work, they need to be intersecting circles, right? So it's the 2 points of intersection where these both of these circles, both of these circles have these 2 points of intersection, which incidentally means that if you're in a two-dimensional satellite world and you want to be able to determine where you are from a certain number of satellites, 2 is not enough, because the problem here is that if you know this information for these 2 satellites, you could be in either up here, come on, up here, or you could be all the way down here. And so you would need a third satellite that hopefully will give you some clarity as to where you are. And so that's an interesting property. Of course, you could have this, and then you're screwed. It's just the same, it's the same problem as before, right? There's no way to be satisfying all 3. And that's where we're headed. Unfortunately, this is the most computational unit of the semester, which means that we're going to be doing a lot of calculator stuff, and it's going to involve a word that I'm sure there's people in the room who hoped that they would never hear again, which is trigonometry. I share that, frankly. I don't like trig. Nevertheless, we're going to do it, and then we're going to get on to much more interesting stuff. There is one announcement that I am supposed to give you before you go. It was something that should have been mentioned. But now I don't remember what it was. Oh yeah, this is great. We're going to have quizzes and we're going to have homeworks in this class. Your lowest quiz score is dropped and your lowest homework score is dropped. Okay, cool. Yes, I was supposed to tell you that. It was in the syllabus, so I'm sure that you all knew that already because you diligently read the syllabus and took notes. Have a nice day. Thank you.